Hello everyone. Here in this video, we want to find out the resultant magnetic induction at a given point. This is the point in our diagram, in our situation where there are two magnets involved. One is this magnet, another one is this magnet. Both of them are having same magnetic moments. I'm just assuming like they are identical magnets. On this point P, who is at a distance D from the center of their combination, we want to find a resultant magnetic field. Let's try. Let's see how do we solve this problem, right? So let's first think of this magnet. This is the first magnet. Let me consider this first magnet, horizontal magnet. At this point, you want a magnetic induction. Therefore, you shall imagine a unit north pole there. One unit north pole. On this unit north pole, this north pole of the first magnet applies a repulsive force that is due to the north pole. On this unit north pole, this south pole applies a force of attraction. But as north pole is close to this point, F north, force due to the north pole, is greater than that of the force due to the south pole. That means F resultant, who is called as magnetic induction due to the first one, is the difference between these two forces. We have already made the derivation. We know that value is, that's an axial line, so mu naught by 4 pi 2m by d cube. What's the direction of that? Its direction is along the direction of north pole because north pole is dominating. So this is B axial, or you can call it like B1. How much of that? How much is that? We have already calculated. Let's think about the second magnet. On this north pole applies a repulsion. So what's the direction? If you draw the line along the site of connection, this is the direction of force due to the north pole. Similarly, this is the south pole who is an opposite pole. On this north pole, this south pole applies a force of attraction towards this direction. They do have certain angle between them. The resultant between them will be, as these two forces are identical in nature because the distances are same, in between them exactly. So this is the direction of the B, which is called as B equatorial. So what is the B equatorial? For this bar magnet, this line becomes a equatorial. For this bar magnet, the same line becomes an axial line. So for the due to the first line, you will get an equation that is due to the axial line, whereas for the second line, you will get the magnetic induction due to that of the equatorial line, mu naught by 4 pi m by d cube. We have derived these derivations earlier. You know these derivations, or you can refer to the previous video. So if you consider this point, on this point now, there is B axial and B equatorial, both are acting and they two are perpendicular to each other. So what is the resultant is, can say B on that point is resultant of that two, B axial square plus B equatorial square plus 2 B axial B equatorial cos 90 as per the parallelogram. Cos 90 is 0, therefore all this term becomes 0, so the value is root of B axial square plus B equatorial. We know the values of both B axial and B equatorial. I can just substitute them. Root of mu naught by 4 pi 2m by d cube whole square, that is this value, plus mu naught by 4 pi m by d cube, that is this value, the second value, whole square, and the square root. So if you simplify this, mu naught by 4 pi 2m by d cube, all that what is common is, you can say There are many common things here, right? So I will just rewrite it as mu naught by 4 pi m by d cube is in common both for this square as well as the root. So I can write it outside the root. Remaining things in the root is root of 2 square plus here is a 1 root of 1 square, that is root 5 times of mu naught by 4 pi magnetic moment of that magnet by the distance q is the resultant magnetic induction at that point. So we are just using the formulas that we have derived for B axial line as well as B equatorial line. I just want to draw another small diagram to show you the contrast of the same in some another way, right? Let us consider one bar magnet like this, having a north and south pole. Pole strength is M and M. Let us consider another bar magnet here, whose north pole is here, south pole is here, pole strength is M and M. Assume these two bar magnets, even in the previous case, are also short. Now I want to find out magnetic induction, a point somewhere in between them. Let me show you and tell you how it is same or how it is different, right? Just I want you to learn and cross-check this. Yeah. See, this north pole on this point, if you imagine a unit north pole, applies a repulsion. This south pole applies a attraction. But as I told you, F north is more than that of F south. So resultant will be along the F north, that is B axial. As I told you, resultant of B axial will be in this direction. Similarly, on this north pole applies a repulsion. This south pole applies a attraction. This is the direction of B resultant, B equatorial, like the previous case itself. Where is the resultant of that two? Somewhere in between, but it won't be exactly in between because B axial is little dominating. So it will move little towards B axial. That is B resultant or B at the point P. B equatorial is the same value like we have derived in the previous case. B axial is also the same. So root 5 times of B equatorial, like the same derivation, because this is nothing but B equatorial. You can say root 5 times of B equatorial is your answer. So though the diagram looks like a different diagram, your answer actually is the same. Of course, the direction is different because the location is different, right? So even in this case also, the resultant of these two it will tilt a little more towards, so it's not going to be in between. Be careful. It will be more towards axial line. Here it makes less angle, theta 1. Here it makes more angle, be clear. Theta 1 will be greater than that of, sorry, theta 1 will be less than that of theta 2 because it is close to the axial line, because axial line value is 2m by the cube, little higher. That's how we can solve the problems. Even under different places, if you keep the bar magnet in different ways, you can simply follow the same approach of finding the location, finding the direction of B axial as well as B equatorial, and you can also find their resultant. This is how you need to solve the problems. Thank you. Thank you for watching.